Today, I'm happy to share my work on applying automated machine learning in functional genomics. So since the rise of deep learning or more especially convolutional neural networks, it has really revolutionized quite a few of a diverse field of studies. So for example, in computer vision, we can accurately label different objects in a pretty messy or complicated image. And moreover, we can even, in this case, label the left one as a German Shepherd dog versus the right one as a husky. And similarly, we can also accurately label the functional or regulatory elements in billions of DNA letters in the human genome. And this is actually one of the previous works that come from our group. We can also accurately identify which of those transcription factors or DNA binding proteins will bind to which particular junction of this human genome. And none of those works would have been as powerful without the employment of the CNNs. So one of the reasons why CNNs are so suitable for modeling images and genomic sequences alike is that they can apply those convolution operations directly on the raw input with while keeping all those spatial structures. For example, in this case, we can just use this 3x3 convolutional filter and scan it through small patches of images. And in the 1D case, we can just use the 1D filter and scan that through the genomic sequences and identify which part of the sequence is actually functional. However, this powerfulness of this CNN does not come for free. So in addition to the standard DNA hyperparameters, such as the number of layers you want to stack, number of hidden units, and choices of activation functions, there are quite a number of CNN-specific hyperparameters, such as how large you want your filter to be, and what's the step size, whether you want to employ dilation rates, or more recently, because of the introduction of residual connections in ResNet, that also becomes a big part of the hyperparameters that we have to tune. And unfortunately, the performance of CNNs is heavily dependent on their architectures. And indeed, during the past few years, a major focus for the computer vision field has been the search for good model architectures. And there have been quite a few famous ones, such as VGGs and ResNet. So even upon a first visual inspection, we can already tell that they're quite complicated. And indeed, each of them is actually inspired by deep understandings of both machine learning and also the domain knowledge. So it takes a large amount of time and effort for even the experts. And thus, this really imposes a non-trivial challenge for the biomedical researchers who are not conventionally trained in machine learning. So as an effort to resolve this challenge, in 2017, a group in Google first introduced this concept of a neural architecture search. This is the whole concept is really not that new because it's a type of hyperparameter tuning. But for the first time, they were able to show that by employing a searching algorithm, the machines can actually design CNN architectures that is very accurate, that matched or even exceeded the ones designed by human experts. So today, if we look at the leaderboard for this computer vision problem on CIFAR-10 dataset, we can see a lot of them are actually designed automatically by searching algorithm instead of by human experts. So now we want to ask if we can have a search algorithm that can design CNNs accurately tells apart dog versus sheep, why can't we do the same thing for genomics, which is arguably more in need of such help? So here comes our motivations for adopting NAS to genomics. First, apparently, it's inspired by the successful applications of NAS in computer vision field. Second, genomics itself is a big data-driven subject, and every day we're generating mountains of high-throughput sequencing data. However, the computational hurdle of designing high-performance CNN architectures really limits our ability to convert those raw data into some useful biological knowledge. So that's why we propose this new method called AMBER, which is the first automated framework that designs CNN models for modeling genomic sequences. And we also demonstrate that it's useful in practice by comparing into well-established benchmarks. So the overview for this AMBER architecture search workflow is like this. So the input for the search module is a compiled training data. So in this case, we have the one hot encoded reference human genome plus a set of binary encoded labels that represents whether a particular regulatory marker is present or not from a publicly available ChIP-seq dataset. But really, you can actually use any training data as long as it's pre-compiled. So taking this as the input, we start to design an optimal architecture for this particular training data. And we do this iteratively for each layer. So for example, for the teeth layer in the search space, there are two different components that we need to search for. So the first one is what kind of computational operations we want to use for this particular layer. And in this case, we can choose from convolution, dilated convolution, pooling operations such as max pooling and average pooling. And in this case, we insert a special operation, which is identity that doesn't do any computations, and effectively it just removes this layer. And the second component is illustrated in this red box, which is the residual connections for the teeth layer. That is whether one of the previous layers ranging from 0 to T will have the residual connection added to this layer. And we do this iteratively for 12 layers in this model space. And after the architecture search, the output of the search module is an optimal architecture for that fully specifies a convolutional neural network. And we can perform some downstream functional analysis, such as allele-specific binding or GWAS, genome-wide association studies. So the meat of this whole work is really how you search for architectures. So in this work, we leveraged one of the cutting edge method that is actually also one of the first pioneering work in the field, which is called the controller RNNs. So the controller RNN fully leveraged the fact that the neural network's architecture has this autoregressive characteristic, which means the operations and residue connections for a particular layer is dependent on all these previous layers. And we model this dependency by this recurrent neural network, and we sample iteratively the computational operations and the residue connections for each layer until a child network is fully specified. So of course, there are some other existing architecture search methods, and a major competitor for NAS is one called differentiable architecture search. They're also very efficient, has been demonstrated to be efficient and accurate. And there are some more conventional ones, such as genetic algorithms and Bayesian optimizations. So each of those search algorithms have their own strengths and weaknesses. And it is our plan to adopt this in the future under our framework. But for now, we only use this state-of-the-art method called controller RNN. So now we have our searcher in place. We apply it to a genomics task, which is the one that I mentioned at the very beginning of this talk. In particular, for any given 1,000 base pair DNA sequences, we are interested in predicting whether one or more of those 919 regulatory markers are present or not, which is binary encoded. So to more robustly evaluate the searching performance, we applied AMBER 6 times independently, generating 6 of those searched models. So each of the line indicate one run of AMBER. And to ensure a fair comparison, we also randomly sampled architectures 6 times. By that, I mean we uniformly sample the computational operations and also randomly wire the residual connections. For those 900 regulatory markers or features, they can be grouped into 4 categories based on their biological functions. So here is the transcription factor, polymerase, DNAs, and histone modifications. You can see that within each category, our search model is performing significantly better than the randomly sampled ones. So this demonstrates that our searching algorithm is actually working. And another observation from this plot is that we see the search models have a somewhat similar performances across different rounds, while the randomly sampled models have a much larger variation of performance. Again, this is expected because when you randomly wire your neural network, you're equally to get a good performance ones as well as a bad performance ones. So theoretically, the performance could be an artifact of a model complexity. Say if our search algorithm just tends to pick simpler models to avoid overfitting, or just pick more complicated models to better fit the data. And that is not the case because we don't observe strong correlations between the performance and the number of trainable parameters. And if we took a closer look at the best search model, which we call AmberSeq, versus the best sampled model, which we call AmberBase, the baseline model actually has slightly more parameters compared to the search model, but their performance are quite different. Moreover, if you look at the original implementation by human expert in 2015, we can see that the architecture is a lot more simpler. However, the number of parameters is way more than both of these cases. So now we can conclude that there is no explicit link between the number of parameters versus the model's performance, at least in this data set. And our searching algorithm is not producing an artifact because of that. And the architectures is really playing a more important role here. So naturally, we want to ask, what is actually being learned in the controller RNN? So to this end, we plotted the selection likelihood for different computational operations across those 12 layers. And interestingly, we see that convolutional operation with a kernel size of 8 is almost universally preferred across those 12 layers. And this same operation happens to be chosen by human experts in the original DeepSeek implementation. So at this point, our automatic searching algorithm is actually in consistency with the choice of human experts. And another interesting observation is that after layer 7, the likelihood of selecting max pooling starts to increase. We think this is because after extensive use of convolutional operations in the earlier or bottom layers of this network, we have already learned and extracted useful information from the raw genomic sequences. So the controller RNN tends to use max pooling to both regularize the model complexity and also acts as a feature selection so that we can have a better performance at the output level. As a complementary analysis, we can also look at the embedding vectors that is being learned during this search process for different computational operations. By applying this PCA analysis on these embedding vectors, some interesting patterns start to emerge. So first we see that PC1 separates identity from all the rest of the computational operations. This is in line with our understanding because remember that identity does not involve any computation at all versus the rest of the operations does something. And in the second PC, the operations are ordered sequentially as vanilla convolution, dilated convolution, and pooling operations. Again, this is interesting because dilated convolution will enlarge the receptive field in a way that's similar to pooling operations. At the same time, they will also perform this convolution. So indeed, dilated convolutions are in the middle of convolution and pooling operations. So this tells us that our controller RNN are capable of learning and distinguishing different computational operations that are both different to each other and also the ones that are similar to each other. And we believe this is the key that this controller RNN can design accurate model architectures. So now I'm going to talk more about the downstream analysis for our model called AmberSeq, because we want to show that they are practically useful for the biomedical researchers. So for example, we can benchmark the variant effect prediction using allele-specific binding. So the variant effect prediction is basically just the effect of a variant or the functional consequences of a variant. This task is not simple because in this ocean of, or this haystack of genome-wide variants, the vast majority of them are neutral. And if we want to find the ones that are actually functional, is very difficult. So the way we do this is we analyzed a bunch of ChIP-seq data sets. And by looking at this allele imbalance, as illustrated in this panel here, we can label them as loss of binding or gain of binding. So in this case, if an allele has more ChIP-seq reads compared to the reference, it is a gain of binding event. And vice versa, if it depletes the reads, it's a loss of binding. And of course, we also have a majority of the events that are neutral, so it doesn't alter the binding at all. So by comparing the, so am I seeing any comments from the chat? Okay, yeah, never mind. So by comparing the loss of binding to neutral and the gain of binding to the neutral events, we do see that our automatically designed method is performing significantly better than the baseline model here. And in some cases, they even matched or exceeded the ones designed by human experts. So we want to extend this analysis to more genome-wide association studies. And to this end, we employed LD score regression, which is a method that measures the heritability enrichment of a variant annotation conditioned on a set of baseline annotations. So these baseline annotations are independently generated of our deep learning variant annotations. And we analyzed all available disease GWAS in UK Biobank that passes our stringent quality control criteria. And indeed, we show that 5 out of the 6 disease GWAS traits we analyzed actually shows a significant advantage of the architecture search model versus the baseline model. So again, it tells us we need this automatic design framework to better understand the disease GWAS variant effects. So at the end, I want to show a bit of software engineering side of this work, which is the code, some Python code. So first, if you want to do architecture search, the first thing you need to do is define a model space. And this is fairly simple. You just need to write a Python function that iteratively add different operations to your model space, which is this model space class. Once you have this model space, you can start by building an Amber class. And again, this is done by specifying which component you want to use, because we are building a growing number of different components that are specialized in different things, and you want to just parse a string of dictionary to it. plus some specifics such as the working directory, input output shape, and I'm omitting some specifics here because of the space. And in the end, you just construct this an instance by parsing those two dictionaries and hit run. And then after 70 hours, GPU hours, you will get an optimal architecture for your specific data set. So in summary, we present Amber, which is the first automated framework that can design CNN architectures with high performance. And we show that indeed the searching is working by comparing it to both the baseline models and human expert design models. And when benchmarking with downstream functional analysis, such as allele-specific binding and GWAS heritability enrichment, our automatically designed models also show significant advantages in several aspects. So that's about the first part of my talk. And I want to just quickly show a new component that we have been working on under this Amber framework. So the motivation is really simple because there has been this report that claims that deep learning, and especially the ones with neural architecture search, is increasingly become a major burden for the environment. So it is estimated that training a natural language model with neural architecture search can emit the CO2 as much as 5 cars in their lifetime. And if you look at the total cost, they could be as much as $3 million. So apparently the question becomes, can we do better than this? So yeah, so this is a co-work with one of the graduate students in our group, Evan. So we aim to build a more efficient controller island called ambient. So the philosophy for this is we just train it once, but we apply it many times on different scenarios. Conventional methods will commission this one-to-one relationship between the controller model and a specific task. But here, we're through the introduction of those dataset descriptors that describes the statistical and biological characteristics of a sequencing dataset, we can jointly train a controller model with a set of different datasets. And at the time of applications, we can just generate an architecture based on these dataset descriptors in a very similar zero-shot way. So as a pilot analysis, we applied ambient jointly on these 36 epigenetic datasets. And as a result, we do see that different biological datasets tends to use different optimal neural architectures. For instance, the chromatin openness datasets apparently prefers average pooling as the first pooling layer, while the transcription factor datasets will almost always use max pooling. There are also some transferable parts such as after the first 3 layers, different datasets tends to use more or less the same architecture. So we think this really the first part is some kind of an adapter that can learn to extract information from sequences of different biological properties. And then the later part is transferable across diverse datasets. In the end, we apply this trained ambient model to some unseen held out test datasets. So in this case, we're asking the trained ambient model to generate an architecture without any retraining or fine tuning. As a comparison, we also run the baseline Amber model and see how their reward or the accuracy of the CNN architectures are changing over time. So indeed, by applying ambient, we can save the GPU runtime anywhere from 8 hours to 21 hours with an average of 15 GPU hours and without loss of much prediction power or accuracy. So in summary, we built a new component under this Amber framework by augmenting the controller model with a dataset descriptors. And we show that it's more computationally efficient and substantially reduces the computing power and also subsequently the environmental footprint. And with that, I would thank my advisor, Olga, and everyone in the Transgaia group. And thank you for listening. And I'm happy to take any questions.